everyone. So Charles told me that he couldn't attend the discussion section today because of some medical issue, and apparently forgot to tell you before. And so sorry if you showed up and waited for nothing. And he just sent out an announcement saying that you'll be recording a video for the discussion and making it available, so you can still have some kind of discussion section for that worksheet. And if you have any sort of questions, you're welcome to reach out to him and ask for details, since you didn't have the occasion of the discussion section to do that. Don't hesitate to just reach out to Charles or even me if you have any questions. All right. Otherwise, before we start, you might have seen that I've published the grades for yesterday's quiz, so you can check that out if you haven't already. And I was pretty happy. Yeah, you managed pretty well to do this kind of exercise. I guess the section on the potential was sometime a little bit less mastered, but I mean, we've done a bit less of example on that, so that's not surprising. So for the final review, my solution for that, and I'll try to find the time to actually give you the answer to get the potential everywhere in space, like for all the region of the in the quiz, not only the two outmost region. At first, I wanted to add that in the quiz, but I realized it would. It gets a little bit more complex, and it's also a bit time consuming. So I realized that you guys wouldn't. It was way too long for the 40 minutes, I think. So decided to crop it out, but I think it would be a good exercise to do everything. So I'll try to give you the solution, and yeah, it'd be a good idea to review it if you have time, because this kind, longer exercise would also be, I don't know, if I feel like it would be a good final exercise or something similar. So who knows? Okay. Okay, so let's get started with today's lecture. So yesterday, we introduced the notion of electrical current and resistance. And basically, we've seen that the current describes the rate at which the charge flows through the area of a conductor. So it can be viewed as the time derivative of the charge in a conductor. And we've seen a more microscopic description of this current, including the drift velocity of the charge, especially the electrons in the conductor. And so, yeah, I want to remind that even though physically it's the electrons that are moving, the current is oriented as if the positive charge, so ions, were moving. So it's the direction of movement of the ions, and so this is the direction of the current. And in reality, electrons are flowing into the opposite direction, but since they have a negative charge, it's equivalent. And we've established this relation, which is very important for electricity and called the Ohm's law, and gives us the relation between current, voltage, and resistance. So we have either I, the current is equal to the voltage divided by R, or sometimes it's also common to see it as voltage equal resistance multiplied by current. But I mean, it's the same thing, right? And finally, we've described a bit more the resistivity, the resistance of material, which is I recall an inner property of a component of a material. I mean, the resistance is a function of the resistivity, which is an inner property of the material, and the geometry of the component. So if the components stay in the same material, same geometry, its resistance is a constant of this component. It doesn't depend if we apply a larger voltage, we just increase the current, but the resistance stays the same as its value given by this formula. And sometime, I mean, here the resistivity is given as rho, but sometime you can also, you might find it as a eta here, eta with the Greek letter. So yeah, don't be surprised if you encounter the Greek letter eta instead of the Greek letter rho for the resistivity. Oh, and yeah, forgot this. And we also wrote the Ohm's law as a in the current density form. And so we have the current density J that is equal to sigma, which is the conductivity, multiply by, so sigma is the conductivity, sigma is equal to 1 over the resistivity. And so we have that this Ohm's law for the current density is the conductivity multiplied by the electric field. Okay, so that was for yesterday. And we'll see a few applications of that, a few examples, and then we switch to, I mean, we continue on with the new concept of electromagnetic force. So let's consider a very simple circuit where we have a battery that's supplying a voltage difference of 1.5 volt here. And this battery is just connected to a small bulb resistance that has a resistance, for instance, of 10 ohms. And the bulb, yeah, just for it happened that a light bulb is just, especially in that case of the typical incandescent light, are just a resistor that heats up and emits light too, and that's so electrically it can be seen as just a resistor. And so if we apply this voltage to our bulb, if we look at Ohm's law, it gives us that the current in our system is going to be the voltage applied by our battery divided by the resistance in our bulb. And so it just gives us a current of 0.15 amps or 150 milliamps. And to do this calculation, we assume that the resistance of wires was negligible, was 0. And I mean, that's not perfectly true. We've seen that any conductors has some resistance, but since the goal of wire is to conduct electricity without any resistance, we can assume that this resistance is going to be negligible compared to the light bulb. But yeah, let's, to be sure of that, let's look at this problem and let's try to calculate the resistance of a wire, of 1 meter of wire, electrical wire. So if we're considering wire gauge 20, so gauge 20 means diameter of 0.9 millimeter. So what's going to be the resistance of that? So for that, we're going to use the formula for resistance. So to do that, we need the resistivity of copper, which was, for instance, in the table I gave yesterday. And so we see that it's pretty low because it's a good conductor. So it's on the order of 10 to the minus 8 ohm meter. Yes. So we're basing off this formula for the resistance. So we have the resistivity. So now we need the geometrical part of the resistance of our wires. So if you remember, the longer our wire is or our resistor is, the higher the resistance, and the wider the cross section of the wire is, the smaller the resistance. So we need this cross section. So we assume just a cylindrical wire. So the cross section is going to be just a disk of diameter d, or so we take the radius, which is half the diameter, and we get this area for the wire. So pretty small area, because it's this wire of diameter less than 1 millimeter. And we're looking for the resistance of 1 meter wire. So that's our L. And so we have all our quantities. So we can just plug that into the formula, and we end up with the resistance of 1 meter of wire of gauge 20, which is 0.03 ohm. So see that this is much smaller than, I think it was 10 ohm, the resistance of the bulb, I think. So yeah, you see that indeed it was okay to make the assumption that, and not consider the resistance of the wires. Okay, so we have a cube the side of length A that is composed of material with a resistivity. And see here, the resistivity is given as eta. It's the same thing, just different notation, as it happens sometimes in physics. So resistivity eta. And the total resistance of the system is R. And now we have another cube, same material, but with a, so it's a cube, and now instead of having a cube of side A, we have a cube of side 2A. So what happened to the resistance of the resistance in this larger cube? Is it larger or smaller or the same? Okay. The right answer is the answer number 2. It's smaller. And yeah, the reason for that is if we come back to the formula for the resistance, so we have resistivity multiplied by the length divided by the area. And so since we have a cube, I mean, the length increase, by, so L is equal to A, but A is equal to A square. And so if we increase the area, if we increase the side, we actually decreases this resistance because the area increases faster than the length. Okay, and here are a few examples of resistance. So, and resistors. So typically a resistor is going to be some kind of conductor that has a resistance R. So it's a conductor that's not too conducting, just it's resisting just enough to serve the purpose of dissipating energy. So I don't know if you do lab session of electricity, the resistance you'll see are like those. So it's small resistors with a start and end, and they have a given resistance. And you can know the resistance of each of these resistors by looking at the color code. And then there's a specific law given by the color and the number of the color band, and you can deduce what's the resistance of that. But otherwise, you can also see, thing like coils like that are resistors. Stuff like that you might see, for instance, in your electric kettle to boil water. You have a resistor in it that gets heated by the electricity and heat your water. Typically in a hair dryer, since it's blowing hot air, it's blowing air through an array of small coils that heat up and give you, heat the air around them. And if you zoom on the filament in a light bulb, you see it's just a very small coil here. And since this coil is very small, the energy that's dissipated in the coil is enough to bring it to very high energy. It's emitting light. But yeah, these kind of light bulbs are a little bit outdated now compared to LEDs or even other type of cathode tube light, because those are using a lot of electricity. They're not super efficient to make light. So yeah, this is what I was saying about the color coding of resistors for electric circuits. So there's, it's pretty easy to apply. You have, rule, and depending on the value as a digit, the first digit here give you the multiplier, and then depending on the color, you can use the resistance. No need to learn that, and honestly, I won't be asking you to guess resistance value from those color codes. If you do lab session in electricity, you might have to do it, but otherwise, yeah, it's not something that's super interesting in a physical point of view. But just so you know, that's how you get how you guess or how you know the resistance of a small resistor like that. Okay. And yeah, another point I wanted to highlight is that resistivity in material depends on the temperature. And for instance, in conductors, especially in metallic conductors, the resistance is increasing with the temperature. So if you get your conductor hotter, you will increase the resistivity of your material. Where it's following typically this law, where you have the resistivity at the reference temperature T0, and then you have a coefficient here that's tabulated depending on the material, and then it's increasing linearly with temperature. And the reason for this temperature dependence in metal is that if you remember, the resistivity of conductors was linked to the drift velocity of electrons inside the material. We've seen that, yeah, the electrons get accelerated by the electric field inside the conductor, but because of collision with ions, they're consistently slowed down and stopped because of this collision, and they have to take to restart accelerating, and so they end up moving at a drift velocity that's kind of constant. And so when you increase the temperature in your material, your ions are gonna vibrate more because of the temperature is actually a description of kinetic motion inside your material. And so if it's very warm, very hot, everything is moving around, vibrating. And so if you increase the vibration, it means that you're going to collide more with electrons. And so you're going to slow them down and increase your resistivity. But this behavior is not shared with any type of material. For instance, it's really something that's associated with metals and conductors, because if you're considering semiconductors or even isolators, then when you're increasing the temperature, you're decreasing the resistivity. So you're increasing the conductivity. And the reason for that, so in the semiconductor or isolator case, basically, why are they isolating is because they don't have any free electron that can move around. But when you're increasing the temperature, you are giving a bit more energy. You are putting more energy into your system. And so, this overall kinetic motion and vibration on your atoms make that sometimes some electron can get released, can get free because of they can get enough energy to be released from their atoms and end up being some kind of free moving electrons. Such as in metal, but there would be more a minority. But if you shake more your material, then you lose, you make even more electron loose, and you're increasing your conductivity. And then there's another specific case of dependence of conductivity with temperature. It's the case of superconductors. So superconductors are a type of material that behave, kind of like a usual metal, usual conductor below a certain temperature with a specific resistance, and they conduct electricity, but they're behaving kind of normal. But if you drop below a certain temperature, critical temperature Tc, then they become almost perfect conductors. They have extremely low resistance, and so they're very useful to conduct massive amounts of electricity, or use them to, for instance, do some magnetic floating because of that, because you can get a lot of electricity flowing without any dissipation and without the material getting too hot. But this typical critical temperature is usually very low. For instance, it's around 4 Kelvin for mercury, so very close, pretty close to the absolute zero temperature. And so they require some energy or some engineering to be kept at this very low temperature. And the reason for this drop in conductivity after a certain temperature is associated with quantum mechanics. I really don't want to get into the details of it. One of the reasons is because I'm not very familiar with that. And that's way past the scope of our of this lecture anyway. But yeah, that's interesting to remember, is that resistivity is increasing for metals, but depending on the material, this behavior can change. And that's basically comes back to the domain of solid state physics, which is very interesting, usually very complicated also, and often related to quantum mechanics. So if we have a resistor made of copper, and that we connect in series with a light bulb, so which can also be seen as a resistor. And we connect that to a battery that causes a current to flow and the light bulb to light up. And then we dip the copper resistor in some liquid nitrogen, so very cold material. And so it's lowering its resistance. So what's happening to the brightness of the bulb? So to summarize, we have a bulb resistance connected in series and connected to battery. And then we drop the resistance of the first resistance connected. Okay, you must answer the choice number 1, and that's the correct one. Because if we drop the resistance of the resistor, then the other resistor, since they are in series, we can add them, and so we have R1 plus R2. It's the total resistance plus R, let's call it RB for bulb. And we also have that the current is going to be equal to U over the resistance. And so if we're dropping this, we're also lowering this value. And so we're increasing the current flowing through the bulb. And so we're increasing the brightness. Okay, so that was it for the chapter on electrical current and resistors. But you'll see that this chapter on electromotive force will be very related. It's basically starting to introduce the electrical circuit from what we've seen before. And so you will see that we're still gonna use the concept of electrical current and resistance and apply them to more practical circuits. So do you have any questions on electric current and resistor before we move on to this new chapter? I guess it's not a new chapter, it's just the rest of the same 25 chapter textbook. All right. So we're gonna come back on the concept of the potential difference and the energy brought by what we've called the battery before in the system. So this is something that provides the potential difference and that allows the current to flow in our system, because if you remember, in the previous chapters, when talking about, for instance, Gauss's law, we've seen that at electrostatic equilibrium, there's no electrical current, electric field that can subsist in a conductor. And this is because there's a retroactive loop happening. So let's consider an isolated conductor, or just a conductor by themselves. So if for some reason an electric field arises from in the conductor, then this electric field is going to make charges move inside the conductor, because charges are free to move, especially electrons. And so if there's an electric field arising inside, there will be a force acting on those charges, and they will build up like that to oppose the electric field. Electrons basically are going to move against the electric field. And so this charge buildup here is going to create an electric field E2 that opposes the first one. But as long as E2 is smaller than E1, so as long as the charge buildup is not strong enough, electrons kept being accelerated in that direction and build up to that side, increasing E2 up to the point where E2 and E1 are equal, and there's no net electric field inside, and therefore no motion, no current, and no electric flow, no charge flow in the system. So you see that in order to have a current flow in your system, you need to consistently have something that keep flowing, keep your charges from flowing a force, and that's the role of battery inside electric circuits, is to create this source of energy that enable the charge to keep flowing and keep an electric field existing in the conductor. And so that's where the concept of electromotive force arises. So the electromotive force can be seen as the influence that makes the current flow from low to high potential in a circuit. Indeed, if you look at an electrical circuit, we've said we have something that creates a potential difference from from 2 points here. So we have, for instance, a higher potential here and a negative potential here. And then basically electrons are flowing into that direction, or you have the current flowing from into that direction. From let's say the current, let's consider the electrons. So electrons are starting from the lower potential and are flowing toward the higher potential. But now, it's an electrical circuit, so they are supposed to loop back. But here, we see that we have a high potential and a lower potential. And so we see that electrons are not going to naturally flow from this point to this point. And so electromotive force is actually the influence that takes electrons for the higher potential and make them go to the lower potential. Or so it's more intuitive, just that makes the current flow from high potential, from lower potential to high potential. So the EMF is the kind of the pump that's driving the system and bring the charges from low potential to high potential, and consistently supplying the system with charge that are in a high potential that can go down the potential gradient. So usually this EMF is written in this uppercase script E kind of shape. So it's not a normal. It's different from the electric field. It's just kind of this fancy E. And typically, we call what's causing the EMF source of EMF. So just some vocab. So don't get things mixed up. The EMF is kind of the influence that bring the charges against the potential, and battery is the source of this EMF. And so you see an EMF is actually homogeneous to the potential here. So we measure the EMF as the potential. Basically, it's how much potential this system, this source of EMF is giving to the charges so they can go down this potential drop. And so you see that since EMF is homogeneous to a potential, even though it's called electromotive force, be careful, the EMF is not a force. It's equivalent to a potential. So why is it called EMF? It's just a historic name. It's been, electricity has been studied for a long time, and when it was the name of that had been given to this phenomena, bringing charges against the potential to keep the current flowing. Okay, and so if you have an ideal EMF source, then your EMF won't have any internal resistance, and so you can assume that the internal EMF, electromotive force, will be exactly equal to the potential at the end of your device. And so if you have a resistor somewhere in your system, then the current will be exactly equal to, the potential will be equal to the current multiplied by the resistor in your system. Okay. An analogy that could help you understand what the EMF is, it could be seen as the lift when you're skiing on slope during winter. When you're skiing on slope in the mountains, you're going down a gradient of potential. You're going up the mountains, and then you're sliding down, and because of the gravity, you're just naturally sliding down. But then when you get to the bottom of the slope, you cannot just loop back naturally and continue driving currents in your day of skiing, because now the potential is oriented so that you cannot go easily up. And so the EMF would be the lift bringing you up the slope so that you can go down the potential again. That would be an analogy for the EMF. Okay, and we've seen that in the ideal case, the EMF was just equal to the voltage difference, the potential difference between the two endpoint of the device of the two. So, for instance, the point A and B. But in real life, as we've seen, even wires have some internal resistance. And so EMF sources will also have some internal resistance inside of them because of their components. And so we usually describe an EMF source as the EMF electromotive force. So really the force that can drive, the inner force that can drive charges against the potential. And then we add the internal resistance of the source. And so that gives us the terminal voltage between the two endpoints of our device, which will be the EMF of our device minus the potential associated with the internal resistance of the source. And so if we come back to the situation where we have our EMF source that's connected to a resistor somewhere, then if our EMF has an internal resistance, now the current that will be going through the resistor will be modified by the internal resistance of our EMF source, and we have to take that into account. That gives us the total current that resistance is modified. And it seems like instead of having the lone resistance in our system, kind of seems like we have in small resistance are associated with our EMF source. So that would be EMF source is this box, and it's made with the ideal EMF and the small resistance. And then we have the external resistor. And so we see that we can just, it looks like it's just two resistors in series. And so we can add the resistance of the two resistors and end up with the current here, given by the potential difference given by the EMF and the resistance. Okay, so this is just to show you different electric components that we will find in different circuits and how they are usually showed. So usually, just if it's a solid line, means that you can see it as wires, so it's a conductor with negligible resistance. Then resistors, they're showed either those small dent oscillation here, or sometimes, for the sake of simplicity, just a box with R inside. Here, these describe usually a battery or more generally a source of EMF. So we have a longer vertical line that represents the positive terminal, and then the smaller, thicker line represent the lower potential. And then if we consider a real source of EMF, we can draw them with the ideal source of EMF plus a small resistance added beside them. And then you might also encounter those V in a circle and A in a circle, and these are measurement instruments. So this is a voltmeter. So we measure the potential difference between its two ends here. So we measure the potential difference between those 2 points. And typically they have very large resistance, and so no currents go through them. So if you want to measure the potential difference in a circuit, usually it's better to plug them in parallel, so you don't just block the whole electrical current from your system. And this would be an ammeter, so to measure the current in your system. And so this time, to measure the current has to flow through them. And so they have to be put in series in your system to measure the current that flows in through them. Okay, let's apply this to a real life example from your textbook. So we have this situation. Let's start getting a little bit more complicated than what we've seen until now. So we have an EMF source here. So this EMF has an electromotive force of 12 volts and an internal resistance of 2 ohms here. So we plug a voltmeter at both ends of the EMF source, and we place an ammeter in series with the EMF source and the resistor. So what are we going to read from the ammeter, and what are we going to read from the voltmeter? So first, let's get started with, if we come back to our drawing here, we see that the voltmeter is placed at this position. And we don't, we know the potential difference at the end of the ideal EMF source. And so we don't have this. And so to access it, we need to retrieve the current flowing into the system so we can know either what is the current, what is the voltage going between A and B, or the voltage between A prime and B prime. And since they seem connected, they might be similar. So let's compute the current. And yeah, also it's something I wanted to add. Since the current describes the flow of charge in the system, the current has to be the same everywhere in a loop that is in series, because if you have an amount of charge that's moving from here, they're kind of pushing the charges from everywhere. They're pushing bit by bit. And so if you have a current here, you have to have the same current everywhere in the loop. And that's true only for the loop that is closed and in series. So let's get the current in our system. So we've seen that for the ideal, for the real EMF source, we can get that the current flowing through is the EMF divided by the sum of the two resistors, the resistance of the actual resistance and the internal resistance of the EMF source. And that's because our system, for the current can be seen as equivalent, just it's equivalent to our EMF source, ideal EMF source, connected to an equivalent resistors. That's just the sum of the two resistors in series, the internal resistor and the outside resistor. So we just get that the current is equal to the EMF divided by the total resistors. And so we get current that's 12 volt divided by 6 ohms, the sum of the two resistors. So we get 2 amps inside our circuits. And now we have the current flowing in our loop. So we can access the potential between our system. So first, if we look at the potential between A prime and B prime, this is straightforward because we have the current and we have just a resistors. And so V A prime B prime is going to be equal to the current we've just recovered divided by the resistance, multiply the resistance. Sorry about that. And so if we do that, we get 8 volts here between A prime and B prime. And now if we get the voltage at A and B, yeah. I mean, first we could assume, since the amp meter is supposed to have zero resistance because otherwise they would mess with the circuit. So usually emitter can be assumed to have zero resistance. And so since they have zero resistance, the potential difference between B prime and B should be the same. And so this would be that the total voltage here would be the same as this one. And so we get 8 volt. But let's make sure of that. Let's do. So if we use this, this formula for the EMF source, the potential between AB is going to be the IMF minus the current going through the resistor or the system multiplied by the internal resistance. And so that gives us 12 volts minus 2 amps multiplied by 2 ohms, and that gives us 8 volts. So you see that either way, we see that the voltmeter is measuring 8 volts. And this is because there's no internal resistance associated with the ammeter. Okay. Yeah, this example is going to be interesting to see why we need to put the ammeter and the voltmeter, why the ammeter should be in series and why the voltmeter should be in parallel from the potential we're trying to measure. Otherwise, it ended up not being interesting measurement. So let's consider these two cases. So it's similar circuits, but in one case, we put our voltmeter on both ends of the resistor here in parallel with the resistor. In that case, we just put it in series in our loop. So in the first case, the voltmeter measure the thing between here and there. And so here the current is flowing through the system, and we've seen the potential difference at both ends of the resistor is 8 volts. And the current is the same, and so we measure 2 amps in that system. But now if we put the voltmeter inside the system in series, we said that voltmeter usually, the resistance of voltmeter usually is extremely high. It usually tends, it's on the order of 1 mega ohm or 10 mega ohm. And so you could say that it's almost infinity. And so since there's a massive resistance in our circuits, now there's no current that can flow inside because the current is going to be a function of the potential divided by the resistor. And so if we have a massive resistance here, we just have a zero current. And so basically there's no current flowing. And so since there's no current flowing here, we have a constant current voltage because no current is going through the resistor. And so here we have the same voltage A here. And here we have the reference voltage 0. And so we just measure 12 volts here, which is just the potential difference associated with the battery because there is no current flowing. So it can have its use, for instance, if you want to measure the EMF of your battery, then if you look at your system without any current flowing, then you access the EMF of your battery. And it doesn't matter what the internal resistance or outside resistance in your system are because no current is flowing through them. And so it doesn't there's no potential drop associated with the current. So why is it infinite resistance? Basically, it's so that current is not flowing because, yeah, a good question. If we're considering this situation, and let's say, I don't know, this, let's say that this has a resistance of 10 ohms, then you'll see that current is gonna come here and then so flow through there. But since there's some resistance, not I mean there is some resistance here, but it's not massive. So some current is going to flow there too. And actually you can retrieve what part of current is going there and what part of current is going there based on the resistance, because they have the same potential difference. So you could pretty quickly get the amount of current going through there and through there. And so you now see that you are messing with your system because you're drawing some current from your system inside your voltmeter, and you're preventing this current from going into your system. And if and And now if you have a non-zero resistance there, then let's say you passing a decent amount of current through your system because you want to power something, then you have a decent amount of current going through your voltmeter, and since it has a resistance, it will dissipate a lot. And it will dissipate energy, and so you might even burn your voltmeter because of that. So infinite resistance prevents your voltmeter from messing with your with the current in your system, and also protects it from being fried by the current in the system. So we have this system here, just near ideal EMF source and a resistor R. So what ranks the potential V across the four corners of the loop? Right. Yeah, it's choice number 2, because the first thing is, those 2 points here are just connected by a wire. So assuming, wires have no internal resistance or negligible internal resistance, so they have the same potential. They're just basically the same point. And then this point here, A, is connected to the positive side of the EMF source, and so it will have a higher potential. And this is connected to the negative side of the EMF source, and so you'll have a lower potential. And so to clarify things about what's happening to the potential in electrical circuits, we can look at every step how it's evolving in this electric circuit. So we have our EMF source, and so by convention, we just set the potential to be 0 at the lower end and positive value at the positive end of the EMF source. And so let's start from the the negative part of the, the low potential part of the EMF source. So we started from 0, and then the EMF is bringing the potential to a high value of 12 volts here. And then we travel across the wire. There's no resistor, so the potential is not dropping. And then the first resistor. And so because we have a potential across this resistance, we have a drop in the potential associated with the Ohm's law, here. And so we see that we drop because of it's 2 ohm. We get that the potential drop is 4 volts. And then we continue on to wire, constant potential. And then we have another resistor. And now this resistor, assuming again Ohm's law, dropped by 8 volts, and it's connected to the end of the EMF. And so it drops back to 0 and loops back here. And so you see the kind of the potential loop happening in the electrical circuit here because of the resistor and the EMF source. Okay, so one of the main motivation for electricity and electric circuits is, of course, energy and power consideration. We're using electricity in our daily life to power basically everything. I mean, not everything. There's also, I guess, gas for vehicles and stuff like that, even though it's even shifting now to electrically driven cars. But yeah, in your house, almost everything is powered by electricity. And so, of course, it's very important to consider energy and power consideration of electrical circuits. So for electricity, we usually use the quantity that's the power, which is an energy per unit time. And so the power of an electric system is going to be the energy, the potential energy of our system divided by the time. And we've seen that the potential energy, or I guess the potential, was defined as the potential energy per amount of charge. And so we can write the potential energy in our system as the potential multiplied by the charge in the system. And so that gives us Q multiplied by the potential divided by time. And so if we just isolate Q divided by the time, that gives us the electric current if we're just considering a steady state where the current is constant. And so we just have a constant amount of charge per amount of time that's moving, because I was dq dt. So in steady state, you can just say q amount of charge per amount of time. And so, yeah, that shows you first description of your electrical power in your system is just the potential multiplied by the current. That's nice because we've seen those two are pretty easy to measure. They're also kind of easy to retrieve using Ohm's law if we know the EMF of our source. And so it's pretty straightforward to retrieve the power in our system, electrical power. And electric energy is very interesting because it's a good way to bring energy in a very non-localized way. You can bring electrical power everywhere using the electrical grid up to your house, and then use it, convert it into other forms of energy by dissipating power, for instance, in resistors. And so if you do that, typically you'll get, that's the easiest way, just you get electrical current through a resistor, and that's creating heat. But with electricity, you can also convert this energy into light, either by the light emitted by the heating coil in a bulb, or with more fancy ways with LEDs. You can also use electricity to drive motors and transform this electric energy into kinetic energy. And this kinetic energy could also be, then transfers as acoustic waves and create sounds with speakers and stuff like that. So it's really a very versatile way to have energy brought everywhere, and then you can just convert it to the source of energy and the application you want. That's why electricity is really everywhere in our lives. And we can rewrite this power in different ways using Ohm's law. So, just switching either I or V with Ohm's law, we can get that the electric power from a system is either the potential square divided by the resistance, or the current square multiplied by the resistance. So depending on the situation, it might be interesting to use either one of those or the current multiplied by the potential, but they're just equivalent anyway. Okay. And so what's happening in your electrical circuit is that you have energy that is stored in your battery. For instance, in battery, it is stored in the form of chemical. It's stored in a chemical form and then can be converted into electrical form using chemical reaction. And so when it's happening, you're taking energy from your battery and you're adding it to the charges of your system. And then your charges are moving here because of the potential difference. And when they're passing through your resistor, some energy is lost by the charge in the form of thermal energy. And so therefore, they fall to a lower potential. It means that you have a lower potential at this point. And so that creates, because you have a lower potential energy. And so the voltage drop. And after that, some energy will be drawn again from the battery, re-energizing those charges, and the cycle can continue. So let's have a look at an example of this. So we're considering a car battery that have a voltage, delivering a voltage of 12 volts. And this car battery is driving a current through the radio system in the car. So, forgetting about the fancy stuff the radio and stereo system is doing, just can, from an electrical point of view, just consider it as a resistor. And this resistor has a resistance of 30 ohms. So first we can wonder how many electrons pass through the stereo each second, and how much power is dissipated in that stereo. So you see that how many electrons pass through the stereo each second is going to be related to the current, right? So how many current is a description of the charge that pass through the system by amount of time. So let's get the current from Ohm's law. So we have a potential of 12 volts and a resistor of 30 ohms. And so it gives us 0.4 amps. And by the definition of the current, 0.4 amps is equal to the charge passing through the system per amount of time. And so if we want to know how many electrons per second, then we take t equal 1 second, and that gives us q is equal to 0.4 coulomb. So this is now the electrical charge that passes through the system per each second. And so to go from charge to number of electrons, we just divide by the charge of one electron. So 0.4 coulomb divided by the charge of one electron, which is 1.6 minus 19 coulomb. And I mean, it's negative for electrons, but since we're considering a current, everything is positive, and so we're using the positive value of E. And so we obtain a total number of electrons that's 2.5 to the multiplied by 10 to the power 18 individual electrons. So yeah, that's a lot of electrons maybe. And that just gonna starting from a macroscopic measurement of current, and then going back to its fundamental description of number of electrons. And then let's look at the power dissipated in our equivalent resistor. So we have obtained the current I. We also have the potential difference V, so we can just multiply the two of them and get 12 volts multiplied by 0.4 amps equal to 4.8 watts. So roughly 5 watts, which is on the typical order of small electronic appliances. So that seems reasonable. And we could have obtained that using just, for instance, the resistor, and could have just used V square divided by R, and it would have given us the same thing, just a little bit more. I guess you have gets larger numbers and you get a ratio to calculate, but it's basically equivalent, because to get the electrical current, we just use the Ohm's law, and this is based on Ohm's law too, so equivalent. Okay, let's do this little poll. So typically on those kind of batteries, for instance, in cars, they give a measurement that's something like 250 amperes hours. And that's same for your phone batteries, and or if you're trying to buy portable batteries, sometimes they give a number that is in milliamps hours. And so watt is described by this quantities, by this number, by this unit of 250 amperes hours. All right. So the correct answer is the number 3, it's the charge because amperes are coulomb per second. So if you multiply by second, you just get coulomb. And so this tells you how long your battery can support a certain current. And that's interesting because typical use of your system gonna draw a constant current for a certain amount of time. And so if you store a certain amount of charge after this amount of time, your charge will be depleted and you have to recharge your battery. All right, we can stop here for today. If you have any questions, you can ask them now. Otherwise, have a good day and see you tomorrow.